morning, students. This is Ishtiaq Shafi. I'll be teaching some important topics in AC portion. I have already covered the DC portion in the classroom, and I have already given you the assignment regarding AC, some important topics, which I hope that you will submit in Google Classrooms to soft copy, and I will check and assess you on the basis of that assignment. And I'll be teaching here some very important topics which can lay the building blocks for the future semesters. The first one is very important, that is power factor. And in your syllabus, it is active power, reactive power, apparent power. But I want to discuss the relationship between these three components in terms of power factor, which is very much important. So in this class, I'll be teaching some important terms related with power factor and what exactly is power factor, what is the definition of power factor, what are the advantages, disadvantages of power factor, and what are the methods through which we can improve the power factor. So in today's lecture, I will be teaching power factor. First, we'll discuss what exactly is the definition of power factor, what is active power, what is reactive power, and what is apparent power. And these three different types of powers, how it is related with power factor. And then advantage, disadvantage, and what are the various applications and methods through which we can improve this power factor. So definition, if you will see the definition, there are various types of definitions regarding with power factor. As the main definition of power factor is that an electrical power system, the power factor of an electrical AC power system is defined as a ratio of real power absorbed by the load to the apparent power flowing in the circuit. The other definition is that it is a phasor angle between the voltage and current. Another definition is that it is the ratio of the impedance and the resistance. So there are various types of definition. If you can see the power angle or power triangle and power factor, you can see that here P is equal to VI cos phi. What is P and what is VI and cos phi? Here VI, this is voltage and current. The relationship between voltage and current in terms of phase is known as power factor. What is the phasor relationship between V and I, right? You have seen, I will discuss that point in the next slide, that what is the phasor relationship between voltage and current in terms of resistor load, in terms of capacitor load, in terms of inductor load, right? So how this phasor angle defines me the power factor. The next one is the cos phi is equal to kW and kVA. As you know that kW is actually the SI units of active power. Active power is what? Real power, true power. The power which is actually getting consumed in the system, right? kVA is so definition. If you will see the definition, there are various types of definitions regarding with power factor. As the main definition of power factor is that an electrical power system, the power factor of an electrical AC power system is defined as a ratio of real power absorbed by the load to the apparent power flowing in the circuit. The other definition is that it is a phasor angle between the voltage and current. Another definition is that it is the ratio of the impedance and the resistance. So there are various types of definition. If you can see the power angle or power triangle and power factor, you can see that here P is equal to VI cos phi. What is P and what is VI and cos phi? Here VI, this is voltage and current. The relationship between voltage and current in terms of phase is known as power factor. What is the phasor relationship between V and I, right? You have seen, I will discuss that point in the next slide, that what is the phasor relationship between voltage and current in terms of resistor load, in terms of capacitor load, in terms of inductor load, right? So how this phasor angle defines me the power factor. The next one is the cos phi is equal to kW and kVA. As you know that kW is actually the SI units of active power. Active power is what? Real power, true power. The power which is actually getting consumed in the system, right? kVA is apparent power. And apparent power is what? It gives me the how much is the active power and how much is the reactive power in the system. And cos phi is equal to true power by apparent power, or cos phi is equal to R by Z, where R is the resistance and Z is the impedance. So what's the relationship? What's the definition? What's the difference between R and Z? R, as we know, I have already discussed in the class that we discuss this R only in DC circuits, and Z we discuss in AC circuits. So there are three parameters in Z, that is R, L, and C. And in R there is the absence of L and C part because of the absence of change in magnetic field. We don't have change. We don't have change in magnetic field in terms of DC. That's why we don't have L and C part there. Right now, if you will see the power triangle here, if you will see phasor angle, that is phi, that S is the apparent power, P here is the active power, real power, true power, and Q is what? It is the reactive power. So I will discuss the power triangle in the next slide, and what is the relationship between the phasor angle in terms of three different types of loads. I will discuss this in the next slide. So again, I will tell you that there are various definitions of power factor, that it is the phasor relationship between V and I, or it is the ratio of active power by apparent power, or it is a ratio of true power by apparent power, or the ratio of R by Z. R is the resistance and Z is the impedance. Right? So next slide we will discuss what is the phasor relationship between three different types of loads. So in this slide we will be discussing what is the phasor relationship of theta in terms of resistive, capacitive, and inductive. Before discussing that, I have already taught you in the class that resistive or resistance load is what? Energy dissipating load. Capacitive and inductive, they are energy storing devices. They store energy. Capacitance stores energy in the form of magnetic field. In terms of electric field, and inductance stores energy in terms of magnetic field. So energy storing devices are two here: capacitance and inductance, and they store energy in the form of electric and magnetic field. That's why they generate or they absorb this reactive power, because they they get this reactive power from these stored energies, right? And resistance is simply energy dissipating device. It does not store any energy. Having said that, if you will see now the power triangle here, S is the apparent power, R is the real power, and Q is the reactive power. Now if you will take the resistive load, the theta here in resistance is equal to 0. If it is 0, that means reactive power is equal to 0. If reactive power is equal to 0, that means apparent power is equal to real power. Apparent power is equal to real power. Now if you will go by the definition, power factor is equal to active power by apparent power, then at that time it is equal to 1. Right? Now in capacitive load, the current phasor leads the voltage phasor by certain angle. If it is pure, then it is 90 degree. So this is leading power factor, right? So in capacitor you have got leading power factor. Why it's leading power factor? Because your current phasor is leading the voltage phasor by how much? Can be theta. If it is not pure, if it is pure, then it is 90 degree. In inductive is opposite of capacitive. Opposite of capacitive means that the current phasor is lagging the voltage phasor by some angle. If it is pure, it will be 90 degree. And the power factor is said to be lagging. Why it is lagging? Because the current phasor is lagging the voltage phasor by some angle. So here you have got three different types of loads: resistive, capacitive, and inductive. Now if we will see capacitive and inductive, right? Now the question arises about the theta. If in capacitive, the current phasor is leading, but cos theta, if you will see cos, like the maximum value of cos theta is equal to 1, that is when cos 0 is equal to 1. That means theta is equal to 0. That means cos, the maximum value of cos is equal to 1 when theta is 0. That is in resistive. So maximum power factor is always a resistive load. But in capacitive, if you will see, there is a phasor relation, there is a phasor angle in 0 to 90 degree. So it varies. It can be like 0.8, 0.6, 0.7, 0.8, 0.9, and 1 is the maximum value. But here the power factor is leading. Why? Because the current phasor is leading. That means the power factor will be always leading. That means if you connect capacitance in parallel with the load, it will always increase the power factor. But this is opposite in case of inductive. Why? Because it has got the lagging power factor. Why it has got the lagging power factor? Because the current phasor is lagging the voltage phasor. So the value is 0 to 1. That means it will be 0.6, 0.7, 0.4, 0.3. And if you connect inductive load across the load, then it will decrease the overall power factor of the system, right? Again, I want to tell you one thing, that the maximum value of power factor is equal to 1 and the minimum value is equal to 0. So again, in this slide, for resistor load, the power factor is equal to 1 because the phasor angle is equal to 0. In capacitor load, the phasor angle lies between 0 to 1. But since the power factor is leading, why? Because the current phasor is leading. That's why it always increases the overall power factor of the system. In inductive load, it always decreases the overall power factor of the system. Why? Because the power factor is lagging. Why the power factor is lagging? Because the current phasor is always lagging to the voltage phasor. So in the next slide, we'll be discussing this power angle in terms of real power, reactive power, and apparent power. In this slide, I will be discussing active power, reactive power, and apparent power. As you know that active power is the real power consumed in the system. It does the actual useful work for the system. Now, if you will see the power angle, it's a very important power angle for the definition of active power, reactive power, and apparent power. If you will see now, apparent power is what? Apparent power is the total amount of power in the system. It consists of both active power as well as reactive power in the system. Real power, and it is measured in volt amperes. Apparent power is always measured in volt amperes, and it is denoted by the capital letter S. Real power, it is also known as true power, real power, and it is measured in terms of watts. This is the actual power which actually gets consumed in the system. But this real power does not constitute any reactive power in the system. It is simply what? It is simply a true power measured in terms of watts. But it does not give the concept of reactive power. Apparent power gives us the concept of what? Active power plus reactive power. But real power gives a concept of just how much amount of power is being consumed in the system. And third one is the reactive power. Reactive power is what? Reactive power is actually the power that supplied by the load towards the source. It does not get consumed in the system. It simply flows from load to source, source to load. It does not get consumed in the system. It induces loss in the system. Now, if you will see by the diagram, if you can see that more the reactive power in the system, more the reactive power in the system, listen carefully, more the reactive power in the system, lesser will be the power factor. Right? It can be seen. See, now, if you will see the resistor load, if theta is equal to 0, then what's the relationship between, if theta is equal to 0, how much is the reactive power? 0. At that time, how much will be the power factor? It will be equal to 1. So we can say that when power factor is equal to 1, reactive power is 0. So we can conclude that there is an inverse relationship between what? The reactive power and the power factor. More the reactive power, less will be the power factor. Lesser the reactive power, more power factor. If reactive power is maximum, then power factor is minimum, right? If power factor is maximum, reactive power has to be minimum. Reactive power is not the useful power. It is simply getting generated from the load centers, usually from inductive and capacitive loads, and it simply flows what? It simply flows from source load, load to source. It does not constitute any useful work in the system. So in the next slide, we'll be discussing what are the advantages of having power factor and what are the various methods through which we can improve the overall power factor of the system. So in this slide, we'll be discussing what are the various advantages of having lesser power factor. As we already studied that the maximum value of the power factor is equal to 1 and the minimum value is 0. So why we have to improve the power factor, right? Why power factor is so much important in electrical circuits. So we will discuss if the power factor is on the lesser side, what will be the various disadvantages for the system. Before I will discuss this advantage of power factor, I want to tell you that if you will see power plants, they have got the inductive load always. And now you are raising the question, why, sir? There are three types of loads, why only just inductive? Now, if you will see that in any power plant, there are active resistive capacitive inductive loads. But the majority of the loads for power plant is from the industries. Industries constitute near about 80% of the total load on the power plant. So if you will go to the industries, what exactly is inside the industries? It actually consists of motors. Motors consist of inductive loads. So for inductive loads, the power factor is lagging. So we will always start with that the power factor is lagging. Why the power factor is lagging? Because majority of the loads on the power plant is of inductive nature. So we'll discuss what are the various advantages of this power factor. Why we want to have power factor on the higher side. Power factor should be always equal to 1 or towards 1 or on the higher side. See, power factor, first advantage is load current. Power factor is inversely proportional to the load current. What is load current? Load current is actually that type of current which flows from source load. If you are running any load on the source, it will extract the load current from the source. So if the power factor of the load is on the lesser side, what will happen? It will extract more current. Why it will extract more current? Because power factor is inversely proportional to load current. That means more the load current, lesser is the power factor, or lesser the power factor, more will the load current. So as you know, the power factor is already on the lesser side. That means it will extract more load current. If it extract more load current, then there will be more losses across the system, which is not good. We want that losses should be on the lesser side. Second is equipment sizing. If you will see by the definition that power factor is equal to active power by apparent power. Now, if you will see the apparent power will be equal to the active power divided by power factor. Now, that means apparent power is inversely proportional to the power factor. Apparent power is inversely proportional to the power factor. As you know, that most of the machines reading is in volt amperes. So we will see if the power factor is on the lesser side for the machine, then what will happen to the kVA? What will happen to the volt ampere apparent power? It will increase because it is got the inverse relationship. So lesser power factor will increase the size of the machine. Why it will increase the size of the machine? Because its power factor is less, the size of the machines is larger. Why? Because the apparent power rating of the machine is on the higher side. Why the rating of the apparent power is on the higher side? Because power factor is less. Why is power factor is less? Because it is inversely proportional to the power factor. That means lesser power factor, more apparent power. More apparent power means more size of the machine. So it affects the cost of the system. Third point is the size of the conductor. As you know, in the conductor there are two parameters. First one is the insulation, second one is the conductor. Right? The size of the insulation is predicted by is indicated by the voltage rating of the system. And the size of the conductor is depicted by how much current is flowing through the system, which is known as current ampage. That means more current means we have to keep more size of the conductor. Less current means we have to keep the less size of the conductor. Now, if you will see, power factor is inversely proportional to load current. Power factor is inversely proportional to the load current. That means lesser power factor means more load current. If there is more load current in the system, that means what will happen to the size of the conductor? Will it increase or decrease? It will increase because the load current is higher. So the size of the conductor is always increasing for the power factor which is on the lesser side. Fourth one is efficiency. See, if power factor is on the lower side, there will be much more load current from the source. So there will be much more losses. If there are much more losses, that means the efficiency of the system will get decreased. So we want to increase this power factor. Now, in the next slide, we'll discuss the ways through which we can increase the overall power factor of the system. In this slide, we'll be discussing what are the various methods through which we can improve the overall power factor of the system. Right? As you know that for inductors, the current phasor is lagging the voltage phasor. If it is lagging, what happens to the overall power factor? It decreases. Now, the case is opposite in case of capacitors. What that means, the current phasor is always leading the voltage phasor. It is opposite to that of inductor. Now, if you have to increase the overall power factor of the load centers, we connect these capacitors in parallel with the loads. Why? Because they have got the leading power factor. Leading power factor means that it increases the overall power factor of the system. Why it increases the overall power factor of the system? Because the current phasor is always leading the voltage phasor. Now, if you will connect in parallel the capacitors with the load centers, if you will have the phasor diagram, you have seen that the phasor diagram for the inductor is that the current phasor is lagging the voltage. Now if I will connect this capacitor in parallel with the inductor, what will happen? It will have the phasor angle exactly opposite to that of what? Exactly opposite to that of inductor. Now if you will take the resultant of this phasor, it means that the overall phasor will be towards the voltage phasor. If the voltage phasor is towards the if the current phasor, if the resultant current phasor is towards the voltage phasor, the overall power factor of the system will get increased, right? So how it gets increased? Because we connect the capacitors in parallel with the load centers, their overall resultant current phasor is towards the voltage phasor. If it is towards the voltage phasor, the power factor is equal to much more higher. If you will recall the diagram for the resistor load, what happens to the current phasor? It is parallel. It is parallel to the voltage phasor. So we can conclude here, if the phasor angle difference is lesser, that means the current phasor is more towards the current phasor. The current phasor is more towards the voltage phasor. What will happen? The overall power factor of the system will increase. It will go towards the one lesser, because it will have lesser phasor angle. Now, by connecting the capacitors in parallel with the load centers, the resultant current phasor is more towards the voltage phasor. That means the phasor displacement is lesser. It is equal to like 10 degrees, 15 degrees. So it improves the overall power factor of the system. The second is synchronous motors. Synchronous motors are also known as synchronous condensers. It has been seen for synchronous motors, they have got the leading power factor. Leading power factor means that they always have the current phasor which is leading with the voltage phasor. If it is leading with the voltage phasor, if you will connect these synchronous motors are running without any load. We don't put any mechanical load on the synchronous motor. Uh, we also call them as free floating. Free floating means that we don't put any mechanical load on the motor. As we know that motor is what? By definition, we supply we supply the electrical energy and they give us the mechanical energy. But we don't put any mechanical load on the motors. So synchronous motors connected without any mechanical load, connected in parallel with the loads, they increase the overall power factor of the system. Why they increase the overall power factor of the system? Because their VI phasor, if you will see, they have got the current phasor leading the voltage phasor. So in the next slide, we'll be discussing some important terms related with electrical engineering and AC portion, and why we have the different types of phasors, why there are no phasors in DC circuits, but it is in AC circuits. We have already connected to the Google Class. If you have any questions regarding today's lectures, you can put your questions there so that we will have much more understanding of this topic. Thank you so much for watching this slide.